Okay, so here's our first example of evaluating a double integral where we're going to use polar coordinates to do the evaluation. Now you can get away without it in this example, but it's not particularly easy to do this in the method of 15.2. So let's see what we can do with polar coordinates. We're doing the double integral over a region R of this function 2x minus y dA. And R is described as the region in the first quadrant enclosed by the circle x squared plus y squared equals 4, and the lines x equals 0 and y equals x. So as usual, you want to sketch this region. We're in the first quadrant only, so that's all I need to worry about. Okay. All right, now this is the circle centered at the origin with a radius of 2. So we're only in the first quadrant. It's going to look like a quarter circle. 2, 2. And looking at the lines that we're supposed to use to bound this region, x equals 0, that's the y-axis. Y equals x is a line passing through the origin with a slope of 1. So that's y equals x right there. And here we have x equals 0, the y-axis. Because the slope is 1, this creates a 45-degree angle with the positive x-axis, or pi over 4 radians. And the region we want is the one bounded by this quarter circle, this vertical line, and this line right here. So this is actually our region R. If I'm thinking of this region in polar coordinates, any point in this little slice right here in polar coordinates is going to have a value of r between 0 and 2, which you can kind of just see by inspection. The angle that makes up this region for any point in this region is going to be an angle between 45 degrees and 90 degrees, or pi over 4 radians and pi over 2 radians. So describing this region R as a set, it's the set of all r theta such that r is between 0 and 2, and theta is between pi over 4 and pi over 2. All right. So to make the conversion into polar coordinates, again, this is what we have to do. You have to take or use r cosine of theta, r sine of theta, and use them as substitutions in the x and y in your f of xy. And then dA becomes r dr d theta. So, and then our limits of integration are the limits for theta and the limits for r right there. So looking at what all this turns into, my outer integral with my limits for theta, that's going to look like pi over 4 to pi over 2. My inner integral is going to look like 0 to 2, the limits for r. All right, now the function that we're integrating is 2x minus y, 2x. X becomes r cosine of theta. So this is 2 r cosine of theta minus y, which is r sine of theta, r dr d theta. All right. Now, to evaluate this integral, notice that if I were to factor the r out of here, I'd end up with an r squared, and what remains in parentheses is only a function of theta. So we can use that property that we talked about, where if the function that we're integrating can be written as a product of two functions, one for each of the variables, then you can separate this into two single variable integrals that you multiply. So that means I can write this as the integral from pi over 4 to pi over 2 of 2 cosine of theta minus sine of theta d theta times the integral from 0 to 2 of, remember this r was pulled out, multiplies with this r to become r squared dr. Okay? that's pretty easy to solve now. So this becomes 2 sine of theta plus cosine of theta from pi over 4 to pi over 2. Here we have r cubed over 3 from 0 to 2. Move that out of the way. All right. And then evaluating this, we're going to end up with, this becomes 2 minus 3 root 2 over 2. After evaluating this from pi over 4 to pi over 2, this 0 is just a 0 when we plug it in, so we don't need to do anything special with that. This becomes 8/3. Okay. If you multiply that out and simplify, you can represent your answer this way: 16/3 minus 4 root 2. It's equivalent to that. All right, so that's our first example with polar coordinates. Let's try another example. Okay, for this one, we're looking for the volume of a solid inside of a sphere and outside of a cylinder, given by these two equations here. I struggle with the three-dimensional drawing, as you know, but I'm going to attempt this one because you kind of need to see what's going on here. So in 3 space, we have a sphere. It's going to have a radius of 4. And I'm not going to be too concerned with the labels quite yet. I just want to attempt to draw a sphere. So here's the trace of this sphere in the XY plane. It's already not looking very good. Let me attempt the trace of this sphere in the in the XY plane, or the YZ plane. And then that sphere, if you can imagine that, is three-dimensional. That's what this equation is. The radius of this is going to be 4. Let me just put a 4 there. In addition to that, we have this cylinder, x squared plus y squared equals 4. Notice the cylinder is going to have a trace in the xy plane that looks like the circle, x squared plus y squared equals 4, so it has a radius of 2. Make that a 2. And being a cylinder, it's going to allow z to vary here. Okay. And it extends infinitely in both directions, but yeah, so that does not look very good, but hopefully you can kind of see what's going on there. So again, if we read this carefully, we're looking for the volume of the solid inside the sphere and outside the cylinder. So in my messy drawing, we're outside the cylinder but remaining inside the sphere. Now, for problems like this, you really want to use symmetry to your advantage. An issue that we're going to run into is the fact that z is not really a function of x and y. If you look at the sphere, it fails the vertical line test. So what we have to do is break the sphere into 2 parts. If I only work with the top half of the sphere, so my sphere, let me say top of sphere, or top half of sphere, is going to have the equation z equals the square root of 16 minus x squared minus y squared. Solved this for z, right? Normally you'd have a plus or minus. The minus, if I put a minus out here, that's the bottom half of that sphere, the bottom hemisphere. So what I'm going to do is find the volume between the top half of the sphere and this cylinder, and then use the symmetry of this image to just double that, and that's going to give me the total volume that I actually want. Okay, so in order to do this, we need to know what region we're integrating over, and you can see in my xy plane I have this annulus, this thing that looks like a ring. So I'm going to sketch that separately in the xy plane. One circle has a radius of 2. The other circle has a radius of 4. Okay, and that's the region R, we're calling it R here, that I want to integrate over. r in polar coordinates, r theta, r takes on values between 2 and 4 for all the points within this annulus. So that's going to be the interval that I use for r. Theta can go from 0 to 2 pi. Notice that this annulus goes through all 4 quadrants. So that's what we use for theta. Okay. All right. So let's move up and remember this. I'm going to move up to see what to do. So I want to integrate this function, because notice the sphere is really what represents the surface that's above this annulus that we're looking for a volume underneath. The purpose of the cylinder is just to carve this hole out in between, but it's really the sphere that's above this region R. So that's what we need to integrate. I'm looking for the double integral over R of the function root 16 minus x squared minus y squared dA. And to convert this into polar coordinates, can't see it now, but we just did it. The region R gave us, for our theta, the interval 0 to 2 pi, and for our R, the interval 2 to 4. And then we need to convert this into polar coordinates. Now in the previous example, we substituted r cosine of theta in for x, r sine of theta in for y. But you can get to the same place by remembering that x squared plus y squared is also equal to r squared. That's one of those conversion formulas. So this is a little easier to manage if we just remember that fact. This can be written as 16 minus r squared r dr d theta. And again, don't forget that you need an r dr d theta. That extra r is going to show up here when you make this conversion. All right, so once again, this is actually a product of a function of r with a function of theta. D theta is the only thing with a theta in this entire expression. So I'm going to bring the d theta out to that outer integral. This becomes 0, 2 pi, 0 to 2 pi. That's by d theta right there. Now this integral right here can be evaluated using a u substitution. Notice conveniently that inclusion of the r out here is what's going to make the u substitution work. So if I set u, I didn't give myself much space over here. I'm going to do this part over here. U is going to equal 16 minus r squared. So that du is equal to negative 2r dr. And it's an r dr that I have here, so alternatively I can write this as 1/2 du equals negative 1/2 du equals r dr. So let me actually let's write this integral now. It's going to look like the integral from, I do want to be careful because my limits of integration have to change here as well. So notice, first of all, if I plug 4 in to the r here, I get 16 minus 16, which is 0. If I plug 2 in, 16 minus 4 gives me 12. Okay? And then my function becomes negative 1/2 u to the 1/2 power du. Okay? Evaluating this, here I'm going to get theta evaluated from 0 to 2 pi. Here, because I have a negative in my integrand, remember you can use that negative to switch the order of integration here, so I'm going to do that, and then I'm also going to integrate this at the same time. So I'm going to get a 2/3 that multiplies to this 1/2, giving me, what is that, 1/3? So I should end up with 1/3 u to the 3/2 power, and I used the negative to switch the order of these limits 0 to 12. Okay. All right. Now let's see. This guy right here just becomes 2 pi. This guy right here, if I Plug in a 0, the whole thing goes to 0, so there's nothing really going on there. But then I end up with 1/3 12 to the 3/2 power, which is the same thing as 12 root 12, giving me a little bit of simplifying that I can do here. That becomes a 4. And then I can also pull a 2 out of that. So this whole thing simplifies down to, let's see, 2 root 3 times 4 would be 8 root 3 times 2 would be 16 root 3 pi. Okay, now remember that's not actually the answer. It's not our volume because we need to double that to get the volume of the entire solid that we're talking about. This is just the top half. So my volume is twice that, 2 times 16 root 3 pi, or 32 root 3 pi. That's it.